Hello everyone, and welcome back to Virtual Thermodynamics. So in our last episode, we talked about the Otto cycle and how we can use it to model internal combustion engines. To do that, we need to do what's called an air standard analysis. That involves a series of assumptions. We neglect combustion, so we treat the working fluid like there's no chemical process that's happening, no chemical reactions that are happening inside our working fluid. We assume that the system is always closed. We assume that all processes are reversible, and we assume that the working fluid is an ideal gas. In our last example, we also showed that you can solve these types of problems assuming that that specific heat is variable or that specific heat is constant. So if you haven't looked at our Otto cycle example, I'd encourage you to do that now. But just a brief refresher on the Otto cycle, we know that sort of the difference between the Otto cycle and the diesel cycle is the assumption that we use when we're adding heat. For Otto cycle problems, we assume that we add heat at constant volume. So you can see that in this PV diagram, because as we are adding heat, which happens between state 2 and 3, we're doing that at a vertical line where the volume, which means the specific volume because the mass is constant, is constant. The difference is that when we do the diesel cycle, we'll assume that heat is added at constant pressure. So here, if we look at our PV diagram, state 2 to 3 happens at a horizontal line where the pressure is constant. So if we look at each of our processes, as we go from state 1 to state 2, we're compressing the fluid. So we're putting work in. Now state 2 to state 3, we're adding heat, but because this is now a horizontal line and not a vertical line, we're also producing work. If we remember, for closed systems, we can find the work by taking the integral of P dV. So there is volume under this curve when we go from state 2 to state 3, so we do produce work during our heat addition process. As we move from state 3 to state 4, we get into the power stroke, so we're putting work out, so we're creating work. Now, if you look from state 2 to state 4, there are two processes here where we're generating work. So sometimes diesel cycles people describe as having a two-stage power stroke. Then when we go from state 4 to state 1, we're again exhausting heat to the environment. So again, sometimes when we talk about diesel cycles, we'll talk about having a two-stage power stroke. So as we look from state 4 to state 1, we can do a first law analysis here, right? We know that as we go from U1 to U4, we have this equation. We can divide by the mass, so these all become lowercase letters. We see that this process has no work. It only has heat. So it's what's called a simple process because it has either heat or work, in this case heat. So we know that the heat that we remove from the system is U1 minus U4, just like it was in the Otto cycle. When we put heat in, the story becomes a little bit more complicated. So here we have an expression, but we have Q and W, and this is not a simple process because we have heat coming in and work going out. So we need to find the work as we move between states 2 and 3. We can do that by taking the integral of P dV. Now, the calculus here is not terribly difficult because P is constant, so I can remove that out of the integral. And then I take the integral of dV and I get V3 minus V2. So here I find that Q2 is equal to, or Q from 2 to 3, so the heat addition is equal to U3 minus U2 plus P2 times V3 minus V2. Now, because P2 and P3 are the same, I'm going to split up the P times delta V term into P3V3 minus P2V2, because P2 and P3 are the same thing. So then I'm going to collect my terms by their state number, and I get U3 plus P3V3 minus U2 plus P2V2, all in brackets. Now, you may remember from thermodynamics that U plus PV is the definition of enthalpy, or specific enthalpy, right? So here we can see that as we move from Q2 to Q3, that's going to be equal to H3 minus H2. So we're used to only seeing enthalpy terms when we have an open system, but in this case we see them with a closed system because we have a constant pressure heat addition. So we're using H now, but that's for convenience and not as a signal that the system is open. So now I'm trying to find the net work. So the net work is going to be the work from 2 to 3, which I've already calculated, is P2 times V3 minus V2. I want to find the work as I move from state 3 to state 4. So I do a first law analysis. This is again a simple system, so there's no heat involved here. And I can find the expression for the work from 3 to 4. And I put that into my equation for net work per unit mass. And then I can look at the work in that happens from state 1 to state 2, which again I derive from the first law, knowing that we have a simple process here. I find that this is U1 minus U2, and I put that into my equation, recognizing the signs here. So I'm not trying to play with the signs. I'm just always getting my expressions from the first law, and I'm letting the first law take care of the signs for me. I've color-coded positive and negative terms by green and red. Just like when I was talking about the heat in, I can collect like terms by their state, remembering that P2 is equal to P3. Again, my U plus PV terms become H terms. So my W net equation looks a lot like the Otto cycle, except that U3 minus U2 has been replaced by H3 minus H2. Now we should remember how to derive this equation, but as a tricky shorthand, what I like to remember is that the equations for the diesel cycle look the same as the Otto cycle, except my two states that are on the horizontal line become enthalpies, and the specific enthalpy is H. So if it's on the horizontal line, it gets H instead of U. And that's nice because horizontal starts with the letter H. I can also think of this equation, the net work, as Q in minus Q out, if I take the absolute values. But again, if I'm using the first law, this is Q in plus Q out, and I let the first law tell me what the signs of the different terms are. So for air standard analysis of a diesel cycle, I have equations for net work per unit mass, heat in per unit mass, and heat out per unit mass. I can do the thermal efficiency as net work over heat in, or as heat in plus heat out divided by heat in. Again, it's a plus sign because I'm using the first law, and the signs will work themselves out. Here I have thermal efficiency if I'm trying to calculate that. Now I know my values. I can take, because the net work is Q in minus the absolute value of Q out. So I can simplify this as 1 minus U4 minus U1 divided by H3 minus H2. We could do this with the Otto cycle as well, but just our H3 minus H2 would become U3 minus U2. Again, 3 and 2 are our states on the horizontal line. So I have expressions for the thermal efficiency. Now in the diesel cycle, there are 3 different volumes, which means we have 2 different volume ratios. The first is the compression ratio, which is the same as in the Otto cycle. So this is going to be V1. It's going to relate V1 and V2. I want my compression ratios to be greater than 1. So I put the large volume on top and the small volume on the bottom. We know that the efficiency of the engine is going to increase with the compression ratio. I never ask for this equation on tests, but here we can see an efficiency equation as a function of the compression ratio, and we see that compression ratio is in the denominator of this second term. So as the compression ratio gets bigger, this term that we're subtracting from 1 gets smaller, which means efficiency goes up. Diesel cycles have another volume ratio called the cutoff ratio. So this is the V after combustion divided by the volume before combustion. Again, it's the larger volume divided by the smaller volume, or V3 minus V2. Here, the efficiency decreases with cutoff ratio, which you can see from the same example. So because this is RC to the power of K, and K is larger than 1, then as RC gets bigger, then that negative term also gets bigger. So we'd like to have a large compression ratio and a small combustion ratio if we're looking for high efficiencies. Now let's take a little bit of time and do a diesel cycle example. We have this state table, and we're asked to find the heat addition, the thermal efficiency, and the cutoff ratio for this diesel cycle. First, we'll find the heat addition. So we know heat addition happens between state 2 and state 3. We know that this is not a simple process and that heat and work are both important here. We calculate the work as the integral of P dV. So we know that Q from 2 to 3 symbolically is U3 minus U2 plus P2 multiplied by V3 minus V2. I know that P2 is equal to P3, so I can group these terms by their state number, and I see that Q2 to 3 is equal to H3 minus H2. If I'm doing a cold air standard analysis with constant specific heats, now my delta H becomes Cp times delta T, so that Q is equal to M times Cp delta T. I know the mass. I don't know T2. I know Cp. And I know T3. I'm also asked for the thermal efficiency, so I'll find a symbolic solution for that. I know that this is Q in plus Q out, where Q out is negative, divided by Q in, or 1 plus Q out, which is negative, divided by Q in. I know that Q out is equal to U1 minus U4, and Q in I've already calculated as H3 minus H2. Again, with a constant specific heat, my delta U becomes Cv times delta T, and my delta H becomes Cp times delta T. So I can get this as a function of different specific heats and temperature differences. I know Cv, I don't know T4, I do know T1, I don't know T2, I do know Cp, and I do know T3. So now I'd like to know something about my cutoff ratio. So RC is my cutoff ratio, and it's V3 divided by V2. So I want to run the ideal gas law between state 2 and state 3. That's where I'm adding heat. So I know that P2 V2 over T2 is equal to P3 V3 over T3. I can rearrange that to find an expression for V3 divided by V2. And I know that P2 is equal to P3 because this is happening at constant pressure. Now I don't know T2 and I do know T3. Remembering that P2 is equal to P3. So now I got to fix my states. If I can find my temperatures, then I can solve all these problems because I already have symbolic equations. So the trick to all of these processes that use ideal gases as working fluids is to find the processes that are isentropic. Now state 1 to state 2 happens at constant entropy, so it's isentropic. Because this is a cold air standard analysis and I know the ratio of the volumes, then I use this equation that has K in the exponent and relates my temperatures to my volume ratio. With that, I can find T2. I can use the ideal gas law between state 1 and state 2 to find the pressure P2. So now I know T2 and P2. I can go from state 2 to state 3 and use the ideal gas law. I know that this is constant pressure, so P3 is equal to P2. So I know that V3 over V2 is going to be equal to T3 over T2. I know T3, and now I know T2, so I know this volume ratio, which is my cutoff ratio. That was part C of the problem. Now I'm going to move from 3 to 4, and again I have an isentropic process. So if I know the volume ratio, then I'm going to use this equation that has K in the exponent that relates my temperatures to my volume ratio. I can get an expression for T4. So here's the trick, that V3 over V4 is equal to the cutoff ratio divided by the compression ratio. There's a bit of trickery involved here, but if you check this out at home, you can see that this is true. First, we know that V4 is equal to V1. So V3 over V4 is equal to V3 over V1. Now we're going to multiply that fraction by 1. But the very special version of 1 that we're going to use is V2 divided by V2. So I haven't cheated. I've just multiplied this by 1. And when I do that, I can separate out into V2 over V1 multiplied by V3 over V2, which is the cutoff ratio divided by the compression ratio. So now I can find T4, which is what I need to solve the problem. So now if I want to find the heat addition, I can see that that's just about 83 BTUs. My cutoff ratio, I know, is just about 2.5. And my thermal efficiency is just about 0.6. So that concludes our diesel cycle example. Thanks for joining me on Virtual Thermodynamics.